Hello students, today we will understand the resonance in a much better way. Thing is, we have a misconception that during resonance the amplitude becomes infinity of a driven oscillator. And what is a driven oscillator? Basically, let's understand what is an oscillator. Oscillator is something that oscillates, right? The spring, for example, a mass attached to a spring, or maybe the spring has some mass. So the spring itself is an oscillator. And our LC circuit, an RLC circuit, that is an oscillator, right? These generate the electromagnetic waves which we use for internet and mobile signals and all. Now, a bridge, for example, is an oscillator, and we know that the bridges break under certain periodic forced vibrations, right? We understand that when the driven frequency is equal to the natural frequency of the oscillator, the amplitude tends to rise up to infinity, right? But that's not true, especially when you have a dissipative force. For example, there is some dissipative force for this particular oscillator, right? This is a physical pendulum that oscillates. If I, for example, if I take it to certain, this is the normal position, I take it to a certain amplitude and release it, it basically oscillates on its own for some time and gradually it decays down to zero because there are some dissipative forces. What are those dissipative forces here? One is it is oscillating through air, so basically there is a drag on it because of the air. Also at the hinge point there is some friction, right? So friction, air drag or viscosity and all of these things cause dissipation. So let's call them as dissipating agents and or dissipative agents, and we call the kind of a factor that we introduce to the equation of motion of this oscillation, we call that beta. Beta is basically the decay factor or decay coefficient. Basically that takes into account all the decaying agents present in the situation where they try to reduce the energy of the oscillator. So basically it was at rest, no energy at all. Now I did some work, I gave it some energy and left it. Now the same energy that the system, the oscillator, in the absence of any dissipative forces, tends to oscillate with the same energy that I supplied to it, right? But again, because of the dissipative forces, it loses out the energy gradually. Its motion, the simple harmonic motion or whatever oscillation it is doing, it simply goes away, it vanishes after a period of time, right? So like this, it will oscillate for some time and gradually it will decay down to zero. Now what happens if I give it some force so that I can overcome the dissipative forces and keep on supplying my energy? So like this, for example, my hand is now a driving force, right, or driving agent. Now it provides some frequency. As I move my hand also with some frequency, this physical pendulum will keep on oscillating as long as the driver lasts, right? But then what happens if the driver has the same frequency as the natural frequency of this oscillator? So let's see, if I keep on increasing the frequency, you see the oscillation is becoming more and more violent, right? The amplitude is increasing, right? But it will never go to infinity, especially in a real case, right? So what really happens? So let's understand. If I take a simple example of an undamped oscillator, ideal case, right? An undamped oscillator, you see the equation of motion written here, right? That's we all know, right? Where xm is this amplitude, right? This is the amplitude, and then you have the omega n, which is the natural frequency of that oscillator in the absence of any dissipative forces, right? So if I give it some energy and release it, it will keep on oscillating forever with the same amplitude and its natural frequency. But gradually, imagine if I have given it some forced frequency, right? So in that case, what will happen? In that case, the amplitude that it will gain or it will actually have will be given by the amplitude of the driving force divided by 2 beta omega n. Omega n is the it's going to be 2 beta omega n, where it will have the resonance amplitude. Okay, that you see, the denominator is never zero. For a finite force at the same frequency as that of the natural frequency of the oscillator, the denominator never goes to 0, that means the amplitude never goes to infinity. What is beta is the decay constant, right? So in nature there are decay constants unavoidably, and so we never would have infinite amplitude. However, if the beta becomes very small, if the decay factor becomes very small or 0, then of course it will tend to infinity, but that is not what happens in the practical case. Now understand one more thing. If I have this one oscillating, correct, and my driving frequency is whatever, right? So basically ultimately the oscillator will be forced to oscillate at the same frequency as the driver, that is my hand here, correct, and it will have some amplitude. Yes, so when I give it some force, basically what I'm doing, I'm giving it a force against the damping to maintain its steady state. Now why do I call it a steady state? Because the moment when I try to, for example, let's see, the moment when I try to make it oscillate, let's suppose I'm giving it some oscillation, right? Then I introduce some driving oscillation. So the transition from the natural oscillation to the driving oscillation or the driven oscillation, that takes some time. So that is called what we call transient motion. Okay. So basically this is how it will happen. Even in case it is at rest and I am giving it some frequency which is not its natural frequency, then the oscillator will negotiate with the driver for some time. That will create some sort of complicated motion, and then it will, within a few seconds after the transient motion is over, it will completely start to oscillate with this equation. In the steady state, it will be xm cosine omega t, where omega is the frequency of the driver, right? Here the amplitude would be given by this function, right? By this equation. Xm is square root of fm divided by, you see the terms, one is omega n minus omega whole squared, which is a positive term, plus 4 beta squared omega squared, which is 2 beta omegas whole squared, correct? So this is the amplitude. But then beta being the decay constant, now then this motion should keep on happening with the same amplitude. It will keep on happening till the driver lasts, right? So the thing is, let's understand one thing. If for example, if the driver, most students think that when I am giving it some energy, right, if there is a driver here, SHM driver, and there is an oscillator. Now people think that this driver is basically supplying energy to this oscillating system or the oscillator, right? But they think that it constantly supplies force. Well, it does, but only against the dissipative forces, right? Apart from the dissipative forces, it doesn't supply any energy at all, right? So the energy exploited by the dissipative forces is something that the driver supplies for this exact same amount. So for example, if you have a digital watch that doesn't have much of resistance in its circuitry, in that case, in the absence of, for example, you are not doing backlighting a lot, you are not watching the time a lot, in that case the battery which actually provides the energy lasts for a long period of time. Why does it happen? Because the dissipative forces are very small. So to maintain the oscillation at a frequency other than the natural frequency of the oscillator, the driver does not have to provide any energy, right? It only makes the oscillator oscillate at a frequency which is the frequency of the driver. Now forced without damping, let's consider, imagine that the dissipative, if I make the dissipative force suddenly vanish, right? All the dissipative forces are gone. Can I have a forced damping? Can I have a forced oscillation without damping? Yes, I can. But imagine if the driver continuously supplied energy to an oscillator, even without the absence of, without any damping or the any kind of dissipative forces, then gradual or continuous supply of energy, wouldn't that make the energy of the oscillator infinite gradually? Because it's not losing energy, it's only accepting energy from the driver, so it will keep on gaining energy. And that means we know the formula for the oscillation, total energy of an oscillation, it simply have, let's suppose an equivalent mass spring system, it will have m omega squared into amplitude squared, So as the energy keeps on increasing to infinity with the same frequency of the driver, the amplitude should go to infinity. That doesn't happen, right? That means the driver does not supply any energy to an oscillator if there are no damping agents or decay or dissipative agents. Okay. So here, this is what happens. If the beta is 0, that means the decay factor is 0, no dissipative agents are there, then the amplitude will be exactly the amplitude of the force divided by the difference of the natural frequency squared minus omega squared, which is the driving frequency, and the oscillator will keep on oscillating at the same frequency given by the driver as long as the driver lasts. So now what happens when the driver, if we suddenly take the driver out, right, if we suddenly release it, right, what will happen? Well, whatever energy it was oscillating with, it's not going to lose any energy, it's not going to gain any energy, it will keep on moving with the same energy. However, what will happen, its amplitude, since its frequency is changing now, the moment when you release the force, right, for example, let's see, here I have this one and it's oscillating like this, right? I'm making it vibrate with certain oscillation, yes. Now imagine that I hold my hand steady. Now, what happens? Okay, wait, once again, look at this. I'm making it oscillate with a certain amplitude, right? Let's suppose I suddenly bring it to rest. So its amplitude changes, right? Its amplitude changes. Why? Because its frequency of oscillation changes. From whatever omega it had, it comes back to omega n, right? It comes back to omega n. And once it comes back to omega n, to keep the energies the same, its amplitude changes. And its amplitude changes by a factor which is equal to omega upon omega n. So depending on omega by omega n, the ratio of omega by omega n is going to be multiplied with its existing amplitude so that you can get the new amplitude. That's it. So in case of forced oscillation, the driver does not supply any energy to the oscillator apart from compensating for the loss of energy because of the dissipative forces. That's it. See you in the next one.